Welcome to this lecture on complex analysis. Today we are going to explore a fascinating topic, limits at infinity. In standard calculus, infinity is a direction, a never-ending journey along the number line. But in the complex plane, we treat infinity as a specific reachable destination. Understanding how functions behave at this ultimate boundary is crucial for everything from pure mathematics to designing stable electrical circuits. Let us dive in and see how we can tame the infinite. To understand limits at infinity, we first need to visualize where infinity actually is. Imagine walking on a massive, flat sheet of paper representing the grid of all complex numbers. If you walk in any straight line forever, you leave the paper. Now imagine wrapping this flat sheet upwards to form a sphere, much like wrapping a dumpling. All the outer edges of the paper meet at a single unified point at the very top of this sphere. We call this single top point infinity. The extended complex plane is simply a standard flat grid with this one special point added. Now that we have introduced the idea of wrapping the plane, let us look at it visually. This diagram shows the Riemann sphere. The flat grid at the bottom is our standard complex plane. Notice how points on the flat plane like Z1, Z2 and Z3 are projected upwards onto the surface of the sphere. As you move further away from the origin 0 on the flat plane, the projected points on the sphere move higher and higher. No matter which direction you travel on the flat plane, you always end up at the exact same north pole. This beautifully illustrates that in complex analysis, infinity is just a single point at the top of the sphere. This visual understanding of infinity brings us to a practical problem. Because infinity is a concept and not a standard number we can just plug into equations, we need a clever trick to evaluate limits there. This trick is called the reciprocal transformation. It means replacing our original variable with the number 1 divided by a new temporary variable. Think about it. If our original variable grows infinitely large, the new variable must shrink to exactly 0. This brilliant substitution allows us to rewrite any intimidating limit involving infinity as a simple limit approaching 0. We already know how to solve limits at 0 using basic algebra. Now that we understand the reciprocal trick, let us look at the formal mathematical rules. There are 3 main scenarios we might encounter. The first scenario is when the input goes to infinity, but the output settles on a normal, finite number. In this formula, z is our original complex input variable that is growing infinitely large. The function is f of z, and w0 is the finite number that the output eventually settles on. The double arrow means is mathematically identical to. The variable w is our new dummy variable. This formula tells us that finding the limit as z goes to infinity is exactly the same as replacing z with 1 over w and finding the limit as w goes to 0. Before we move on, let us see this with a concrete example. We need to evaluate the limit of the function 2z plus I over z plus 1 as the variable z approaches infinity. This is a classic case where the input is growing infinitely large, but we want to see if the output settles down to a specific value. To solve this, we will use our first rule, the reciprocal transformation. We will replace every instance of z with 1 over w. Then, instead of trying to calculate what happens when z gets massive, we will simply calculate what happens when w shrinks to 0. This transforms a confusing infinity problem into a straightforward algebra problem. Continuing with our substitution, we now have 1 over w wherever there was a z. As z approaches infinity, our new variable w will approach 0. Now we need to clean up this messy fraction. We find a common denominator for both the top half and the bottom half of the main fraction. By combining the terms, we prepare the equation so that the extra variables can be cancelled out. The denominators of w cancel each other out completely. We are left with a much simpler rational function that no longer has any hidden division by 0 issues. Now we can safely evaluate the limit by plugging in 0 for w. The imaginary part in the numerator becomes 0 and the w in the denominator also becomes 0. This leaves us with 2 over 1. The final result is the finite number 2. This means that as the input wanders off to the infinite edge of the complex plane, the output of the function stabilizes and settles exactly on the number 2. We have successfully evaluated a limit at infinity using the reciprocal transformation. This brings us to the second scenario, which is the exact opposite of the first. The input approaches a normal, finite number, but the output explodes to infinity. Here, z0 is a specific, finite starting point on our complex plane. The formula states that if a function's output blows up to infinity at a certain point, then the reciprocal of that function, which is 1 divided by the function, must shrink to exactly 0 at that same point. This gives us a very easy way to prove that a limit is infinity. Just flip the function upside down and prove that the flipped version goes to 0. Let us put this second rule into practice. For our next example, we need to prove that the limit of the function z plus 1 over z minus 1 as z approaches 1 is equal to infinity. Here, the input is a normal number, but the output is exploding. When a function's output goes to infinity, it usually means the denominator is shrinking to 0 while the numerator stays solid. To prove this formally, we use our second rule. We flip the function upside down and prove that the limit of this flipped function goes to exactly 0. Notice how the numerator and denominator have simply swapped places. Continuing with our flipped function, we are still letting z approach 1. We evaluate the limit by directly substituting the value 1 in place of the variable z. This gives us simple arithmetic to solve. 1 minus 1 over 1 plus 1, which simplifies to 0 over 2. The result is exactly 0. Because the reciprocal of the function goes to 0, the original function must blow up to infinity. This confirms our proof perfectly. We have shown that the output explodes as the input approaches 1. Now that we have seen the first two scenarios, let us look at the third and final scenario. This is when both the input and the output go to infinity at the same time. This formula combines both of our previous tricks. Because the input z is going to infinity, we replace it with 1 over w and let w go to 0. Because the output is also going to infinity, we flip the entire function upside down. If the limit of this flipped substituted function equals 0, then we have successfully proven that the original function goes to infinity as its input goes to infinity. You might be wondering, why does understanding limits at infinity matter in the real world? In fields like electrical engineering and control systems, engineers design circuits that process signals over time. They often need to know if a system's energy will blow up and destroy the circuit or if it will stabilize as time or frequency increases indefinitely. By mapping infinity to 0 using the reciprocal transformation, we can program computers to check system stability without causing overflow errors in the software. It also allows mathematicians to classify poles, which are specific points where a function explodes, even if those points are located at infinity. We have covered a lot of ground today. Let us review the key takeaways. First, limits at infinity in complex analysis treat the infinite horizon as a single reachable destination on the Riemann sphere. Second, by substituting the variable with its reciprocal, we elegantly transform intimidating infinite limits into simple limits approaching 0. Finally, if a function explodes to infinity, flipping it upside down means it must shrink to 0. This powerful technique ensures that we can analyze and predict the behavior of complex functions everywhere, leaving no part of the extended complex plane unexamined. You now have the tools to handle infinity with confidence.